All right, we are going to be working with breaking down radicals. So today we are breaking down numbers into their prime factors so that we can simplify radical expressions, and you'll be able to do it when you can simplify something like the square root of 125. So think about the square root function. When we say a square root, what does it mean to take the square root of a number? So I'm going to give a couple examples and then I'm going to let you answer that question. Think about the square root of 49 is 7 because it's two numbers that are the same that are multiplying up to make the number inside the square root. So we would call this a perfect square. Another example would be the square root of 25. Two numbers that multiply up to make 25. It's the same number. Is 5. 5 times 5 is 25. So when we think about perfect squares, taking the square root of a number means that we're finding two numbers that are the same. So the square root of 16 would be what? It would be 4. So what does it mean to take the square root of a number? I'd like to see kind of in your own words. Okay. We are going to be simplifying radicals. So the examples that we just looked at, you may be familiar with, the perfect squares. The problem is that we're not always going to be working with perfect squares. So there are 3 different ways we're going to look at to simplify radicals. We're going to look at a factor tree, we're going to look at a factor ladder, and we're going to look at perfect squares. So whichever way you kind of lean toward, the whole purpose of this lesson is to just give you an idea of how these things can be done, and then I'll kind of switch through different methods as I solve these, just so that you're more familiar with them. But starting with the factor tree. So the whole idea in simplifying a radical is that we are looking for groups of 2 of the same. And in 49, there is a 7 and a 7, a group of 2, and we use one of those 7s in our answer. In 25, 5 times 5, and we use one of those 5s as our answer. And then with 16, it's 4 times 4, and we use one of those 4s in our answer. I like to tell a little story about jailbreak and how you need partners. So you need groups of 2 in order to break out of jail. So one of those numbers from the groups of 2 gets out. One of these numbers from the groups of 5 gets out. One of these 4s from our group of 4s gets out. So let's talk about a factor tree. The whole idea is that we want to break 72 down into its prime factors. So our prime numbers that we're going to be really using a lot will be 2, 3, 5, 7, and occasionally we'll get to use an 11. For most of the work that we're going to be doing, these are the numbers that we're going to be looking for. We're going to break everything down into 2s, 3s, 5s, 7s, 11s. So you'll see kind of how that works here on our factor tree. And for like kind of a systematic approach to it, I'm going to start with 2. So I'm actually going to write my prime factors here. You'll see in just a minute kind of how this works. 5, 7, 11. And this is just a way of organizing it. You wouldn't have to do this, but it is a way to do it. So I'm going to start just by breaking it down, and when I say breaking down, I mean dividing by 2. So I'm going to think 72, can that be broken down using 2 times a number? And it can. It's 2 times 36. And then I'm going to use a 2 again. Can 36 be broken down by can it be divided by 2? It can. It's 2 times 18. And now again, I'm taking 18. I'm saying, can it be divided by 2? We may not move into any of these other numbers. 2 and 9. And now we're looking at 9. Can 9 be divided by 2? And the answer is no. 2 doesn't work there. So watch. I've used up 2 as much as I can to get 3 prime factors there. I'm now going to move on to 3. Can 9 be broken down by 3? And it can. 9 can be broken down 3 times 3. I guess I should. Okay? And the whole point is to break this down into its prime factors. So every time when I broke down 36 into 2 and 18, that went away. I used it up to make 2 and 18. When I broke 18 up into 2 and 9, it went away. When I broke 9 up into 3 and 3, it went away. So these are the values we're working with here. And if you were to go through and do 2 times 2 times 2 times 3 times 3, you will get 72. That's the whole point. It's the smallest prime numbers that exist within our big numbers. So 72, 2 times 2 times 2 times 3 times 3. And I'll just kind of show this real quick. 2 times 2 is 4, times this 2 is 8, times this 3, 8 times 3 is 24, times this 3 is 72. So all of these numbers multiply up to make 72. You don't have to go through and do that check. I just wanted to explain to you kind of what's happening, what do these numbers mean, and how we got them was by dividing it down by each prime factor. So here's kind of the next important part from our factor tree, is we can look for groups of 2. So remember over here where we had our perfect squares, 49 breaks down into 7 and 7. 25 had 5 and 5. And 16 had 4 and 4. So we were looking for groups of 2. So I'm going to be looking for pairs. So I have a pair of 2's here. And remember what happened. I said one gets caught, one makes it out. So it makes it outside of the radical. I have another pair here. I have a pair of 3's, and that's going to make it outside. And anything that's going together with other numbers that make it out or that get stuck inside are going to be multiplying together. So that's going to be 2 times 3. And then if you notice there's this 2 here that didn't have a partner, that gets rewritten back inside the radical because he didn't have a partner. He couldn't even try to escape. So our last step is we're going to take 2 times 3 and make 6, radical 2. And that's our answer. So that's using the factor tree. I'm going to show you the same problem now using a factor ladder. And these are just different ways of organizing your work. So the factor ladder, again, I'm going to use prime factors, 2, 3, 5, 7, 11. So I'm going to start with 2's. And this is what a factor ladder would look like. I'm going to take 72 and I'm going to put it kind of inside this box. And I'm going to divide 72 by 2. So I'm starting here. Again, I got that 2 from here. This is my starting point. So 72 divided by 2, I'm going to write my answer down here. 36. I'm going to do the same thing. Can 36 be divided by 2? Yes, it can. And our answer left over is 18. And then can 18 be divided by 2? And it can. It gets us 9. And then can 9 be divided by 2? And if you checked it in the calculator, you would get a decimal, and you go, oh no, that didn't work evenly. So we ran out of 2's. So now let's use a 3. Can 9 be divided by 3? Yeah. And it gets us a 3 left over. And then we're saying, can 3 be broken down any further? And it cannot. It is a prime factor. It's one of our prime factors. What I like about the ladder is that it organizes things pretty nicely. When I do the factor tree, I always write my prime factor or my smaller factors on the left side so that it's easy to find. The problem with the factor tree is sometimes if you don't organize it like this, everything gets really jumbled up, and then it's hard to, like I may have had a 2 sitting over here and forgotten that I'd used it, and then it gets left out of my answer and I get the wrong number. So the factor ladder helps avoid that. Again, I'm looking for groups of 2. So I have 2 2's, 1 gets caught, 1 makes it out. I have 2 3's, 1 gets caught, 1 makes it out. And when they get caught, they don't go back in jail. They just disappear. They're sent to a higher security prison. Okay, and then I have this 2 sitting on the outside here with no 1. So he's still stuck inside. Again, we multiply up. 2 times 3 is 6. Radical 2. Okay. Different way of organizing the work, same answer. And then finally, perfect squares. So this one, unless you're really good with using perfect squares, I'm going to recommend, if we were in the classroom and working together, I would be able to kind of help this along. But for the purpose of an online lesson, this may not make sense. So you can just ignore this part. If it seems really confusing, don't worry about it. You don't have to know how to do it. But essentially when we're working with perfect squares, we're looking at, is there a perfect square inside of 72? So I'm going to list some perfect square numbers off to the side here. We have 1, which doesn't really do us much good. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. 5 times 5 is 25. 6 times 6 is 36. 7 times 7 is 49. 8 times 8 is 64. 9 times 9 is 81. 10 times 10 is 100. So we'll just kind of go that high, especially since 72 is not is smaller than our last 2 values there. Essentially what we're doing is we're saying, what's the largest, is there a perfect square inside of 72? And what is it? What's the largest perfect square inside of 72? So it wouldn't make sense to use 100 or 81 because those are bigger. So 72 divided by 64, would that work? And the answer is no. We get a decimal. 72 divided by 49. I guess I'll cross these out as I go. So that was no good. That's no good. 64. 72 divided by 49, if you were to work that out, it wouldn't work. 72 divided by 36. If you punch that in a calculator, it would work. So think if we had 36 times 2 would make 72, and that's a perfect square. So then we would say, well, what's the square root of 36? The square root of 36 is 6, and there's no square root for 2, so it's stuck back inside. So the deal with the perfect squares, look, we got to the same answer, 6 rad 2, 6 square root 2. You'll hear me interchange rad and square root. They mean the same thing. So significantly less work here, But if you're not familiar with your perfect squares, it is kind of more guess and check. This is a like foolproof. You write all the numbers down, you find your pairs, and it works. This is a little bit more nuanced. There's some guess and check. There's some understanding what those things are, so on and so forth. So I'm just going to take us through a couple examples here, and then we'll continue working on these. So I'm just going to do the top 3. So 27, I am going to use a ladder. So I'm going to take 27, and I'm going to say 27, and I'll write my prime factors here so that you can see what I'm thinking through. Well, can 27 be divided by 2? So 27 divided by 2 wouldn't work. So 2 is no good. So now I'm moving on to a 3. 27 divided by 3, and that does work. 3 and 9. Okay. Can 9 be divided by 3? And it can. 3 and 3. And then this is the number that we're trying to break down, right? These are the numbers we pulled out. These are the numbers that were left over. 3 can't be broken down any further. So these are our 3 factors, our prime factors, because 3 times 3 times 3. 3 times 3 is 9. Oops, even though I didn't write a 9. Times this 3 is 27. That's what we started with. So, get rid of all that mess. So I'm looking for groups of 2. I have a pair here, and one person stuck inside the radical. So 1 gets out, and this guy that I put in the box is still stuck inside. 3 square root 3. Okay, for 75. Again, we're using 2, 3, 5, 7, 11. And you just keep, you don't jump around, you just keep using. So for this one, 75, probably a lot of us thought, oh, it's 5, we can use a 5. And you could break it down this way, but I'm going to go systematic again. So I'm going to use a factor tree here. Can 75 be divided by 2? It cannot. Can 75 be divided by 3? It can. 3 and 25. Think about if you have 3 quarters, 75 cents. And then can 25 be broken down with a 3? It cannot. It can be broken down with a 5 though. 5 and 5. So I'm looking for partners. I have a pair here. 1 gets caught, 1 makes it out, and my 3 is still stuck inside. I use my 25 up to make 5 and 5. All right, and our last example. Again, with 45, we could say 5 and 9, if you see that. And then break 9 down, 3 and 3. There's my partners. 3. This guy doesn't have anybody. This got used up making 3 and 3. Square root 5. So it's very possible if you're good with your math facts and you see those things. If you like a good systematic way of doing things, you can always use 2, 3, 5, 7, 11, and just work your way from left to right. Would 2 go into 45? No. Will 3 go into 45? Yes. Okay, so 3 and 15. And then will 3 go into 15? You stay on the same number until it doesn't work anymore. And 3 does go into 15, 3 and 5. Pair of 3s. So 1 makes it out, 5 stays inside. And you saw that I was able to do that with. So the thing with using all the different multiplication terms is, eventually it will lead us to the same answer. So hopefully you found this informative. We're going to continue working with this because it is a skill that you will need, especially if you're going into geometry, but it's a skill you will need for other levels of math.